Okay, so we're going to go ahead and start on the next video for linked lists. This is going to be the second of a series of videos on um, basically the linked list manager. We already did a bit of a video on what I call the poor man's linked list, where you have a node and you manage the node just with simple statements such as working with the next, and you can see that that's kind of ridiculous, and we should have some kind of manager to loop through the next of any node, so that we can work with that instead of this kind of behavior right here, which is totally ridiculous. So the way that that's going to take form is it's going to be a whole nother object that's going to be called linked list, that's going to then manage the nodes that are going to be inside the linked list. So we're going to do kind of the similar thing we did here with a node. We're going to go up here to project, add class, and we can just call this one linked list. And add that, and it's going to have two parts or two main things that the linked list keeps track of, and that's going to be what we call the head node and the tail node. You don't actually need the tail node. However, the tail node makes it easier to kind of keep track of adding to the rear of the list, instead of having to loop through each next node to get to the end of the list and then add to the end in that manner. What a lot of people decide is just to go ahead and keep track of a head node and a tail node, and of course we're going to be adding on to this as we go. So we also want a constructor that needs to be public, and we want to keep these private. We don't actually need accessors for them. We'll just manage those within the functions that are going to be publicly accessible. But when we do have, or when the linked list is constructed, we do want to set head equal to null and tail equal to null. And the very first function we're going to have is a add front function. And essentially the add front function, what it does is it takes whatever is going to be stored in the node, it's going to take that as an argument and it's going to add it to the front of the list. So it's not going to return anything, but it's going to be publicly accessible. And the object that it's going to take is going to be what it is. It's going to be the storage of what's inside of the node. And we may want to give it a different name, but we're able to differentiate between the node storage and the object storage or the function storage fairly easily. So let's go back to linked list management, and the thing that we're going to want to do first off is whenever you do an add front, essentially the way this is going to look is I'm going to go ahead and go into the form code now, and I'm going to instantiate a linked list. And what it has is it has two reference types that are immediately created, one for the head and one for the tail. Let's see, that might be a little too big. Let's bring this one in. There we go. The head is going to start out as pointing nowhere. And let's reduce the size of this guy. And then we're going to have the tail that's going to be pointing nowhere as soon as the linked list is instantiated. And these are reference types. And they're going to have their own address, which is not really important. It's what they're going to point to that is important. And I believe I want to add something so that I can make some notes as we progress here. So now we get to the actual instantiation of the linked list, and that's going to be done from the form. You can do it anywhere in the form if you want, wherever you want. You can do it in form load. You can do it based on a button press, but basically we've already built this form load function that we used in the last video. So what I'm going to do is we're going to actually be working with a while loop that prints the list, but we'll do that from the manager. So when the form loads, we're going to go ahead and instantiate the list. I'm just going to call it my list, and I'm going to say it's going to equal to a new linked list. Now, the way that we're going to actually use this in add nodes is we're going to use the functions that we make publicly accessible, which we've already defined, and we're going to say add front. Now, anything, as you see, it comes up there, anything can be an object. Any data type that you create in C# can be represented as an object or boxed up as an object. And then you just cast it to and from the data type it actually is. So we can just throw in some literal numbers in here, and it will automatically cast to an object, or implicitly cast to the object. So this should be okay. We're going to add number 1 as the first thing, or the first storage piece, or just basically it's a numerical value that we're going to have stored in the node in its storage. And again, it can be anything. It could be another linked list. You can have a linked list be the object that's stored in each node. So you can have a linked list of linked lists and so forth. So we have our first add front, and what we want to happen is when the linked list is instantiated, the head and the tail node or reference type, they're not nodes, they're reference types, they are going to point nowhere. And what we want is, as soon as we say add front and we send it the storage to add to the front, what we can do is we can instantiate a node that we're going to link to with the head and the tail. So let's go to the add front function, and the first thing you do is you know that you're going to have a new node. So just create one and call it end node for new node, and say it's equal to a new node. And what we can do is we have an accessor in that node for its storage. And we can assign it to the storage that's coming through as the argument. So essentially, we take that number 1 that comes in as storage, and we assign it to the new node storage. So the new node is going to contain number 1. So the way this looks is, let me see if I can't get a bit of a diagram here. Here's the number 1 that's coming in as storage. Our next is pointing to 0. And basically, we have a reference type called endNode. And let's go ahead and create that reference type. And it points to address 100. So currently we have head and tail that point nowhere, and end node that points to the actual new node. Let me minimize some of these real quick because they are getting a little bit too big for the screen. It looks like the text isn't going to resize for me. Yeah, let's just reduce that. Okay. And get a little bit of some reduction on these reference types. Okay. So the end node, once we have this line of code run, is pointing to that new node that we've gotten off of the heap that was automatically assigned to us from the operating system. So it's said to point to that end node. Let's see if I can't get my drawing program to work. This is a kind of little overlay to demonstrate that, hey, yeah, this points here. So what we want is we want to have head and tail point to it too. because after all, it's our first link in the list. So we need to assign head and tail to the value that EndNode is storing in it. So essentially that'll be address 100, which is where that new node exists. But first we've got to look at, hey, do we already have links in the chain? And we already know that it's not. This is our first one. But you still have to, that has to be a decision that you need to make. So you're going to actually use an if statement. And you're going to say if head equals null. That means there is no links in the chain. And if head equals null, then it's really simple. You say head equals EndNode. What that does is it takes the value in the new node that is holding our new node, and that is address 100, and it assigns it to head. So now that link is made. So now head points to that new node. And then, of course, since we want the tail, the first one on is also the tail. It's the head and the tail. We want to assign tail equal to EndNode. So what you can do is a little trick here. You can say head equals tail equals EndNode. So essentially, take this 100, throw it here, and throw it here. So now the head and the tail both point to the same location in memory. Let's see if I can't make these a little smaller now. Yep, there we go. Okay. So now what happens then is this function gets done running, and we've made our first connection. And since EndNode is a reference type that points to memory on the heap, what ends up happening to that reference type when it's done, this function is done running, is it's automatically destroyed and it just goes away. So the heap memory is still there, and essentially the head and tail, since they are still memory that is part of the linked list in the lifespan of the linked list, they retain that address to that memory that's on the heap. So it's still there. Okay, so that then takes us to the next bit of add front. What happens when essentially you add another item and now head is no longer null? There's actually something there. So that is easily done because that will be your else portion. So if head is null, then we do this. If it's not, then we have different behavior. We actually need to make some links because we already have nodes present. And that happens when we do something like this. Add another front, mylist.add front, and this time we're going to add 2. So that changes things a little bit. We currently have head and tail pointing to the same node, and but now we're going to be adding one. We're going to be adding one that's going to. Oops, it looks like I got that one a little bit too. We'll come back and do some more drawings here in a little bit. I think I got too big of a pen somehow. Okay. All right, so the new node is created. Head and tail are currently pointing to this guy right here. So add front runs again. Add front runs, and we're inside of linked list add front. We create another EndNode. So that means we have another storage, but this time we're passing in 2. So EndNode is a reference type, just like head. So we'll just take this, copy it, and we'll do paste, and this becomes EndNode or new node, and it's currently pointing to, let's say that the operating system gives us 200. Oh wait, no, that's already used up. Let's say it gives us 800 as the address for that. So that means that EndNode is pointing to that new one, and its storage has 2 in it. So the line that we would draw would just go from here to there. So we get into the add front runs. These lines are done right here. So essentially, these two lines create this new node and assigns ed node the reference data type pointing to that new node as a reference. Now what's going to need to change is, since this is an add front function, that means that this number 2, the one that's holding number 2, is going to be the new front. So what we need to happen is we need to take the head and make it pointing to here, because this, after all, is the new head. We don't have to mess with tail because tail is already pointing over here, and it's going to remain the tail because the add front is the head pointer, because of the very nature of add front, is the only one that needs to be changed. So essentially, the line of code that you would do is you would first assign head to end node. And it's really kind of simple, but you have to make the link between the new node, its next pointer, to this one. Now it looks like I'm going to have to increase the size of these reference types in here because I'm losing some text. Let me go ahead and add to that. There we go. Okay, so the next is just another reference type, just like end node and head and tail, that points to the next one in line. So the next one in line is going to have the address 100. So what we want is we want the new node's next to be equal to the head or the tail. So we got to make that connection first, because because head is what's holding our head. We can't mess with head until we make the connection between these two. So essentially, we're going to do this line of code. We're going to say end nodes next equals head. And since head is got 100 in it as the address, and it's pointing to the old head, what we've done is we've just assigned now 100 for the next pointer reference type, and now what we've got is we've got our link from here to there. Now we're almost done, because then what we have to do is, since this is the new head, we essentially want to assign that and say head is equal to end node. So what that does is it takes the address in end node, which is pointing to the new head, which is at address 800, and it assigns that to head. And now we have a new head, and essentially it's now pointing to our new head right there. And this goes away. That we can erase. Let me grab the eraser. Okay, so head's pointing now here. Head's next is pointing to the next one. Tail's still pointing to the next one, and the function add front is done, and end node is destroyed, and now we have a fully linked list. Let me fix some of these guys, because I got a better marker to use. And now if you notice, tail points to address 100, which is our old head and our tail, and its next points to 0 or nothing, so it points nowhere. Now, and our head now points to the new head, and its next points to the next node in the link. Okay, so that's kind of currently what we have, and if we do another add front, we're just going to get another node out here and the same behavior until it isn't messed with at all. So then that takes us into, well, how do I remove the front? Well, first let's test this. Let's add some kind of print function that'll print the nodes and the information in the nodes. And since we're using a simple data type, let's be simplistic with it. What I'm going to do is I'm going to create a print function, and I'm going to have it take some kind of control for for printing, and I think what we'll do is we'll print it with a list box. And basically what I can do is I can just say, give me a list, take a list box as an argument and call it the list. Now, list box isn't coming up, so what we got to do is we got to include the reference to System Windows Forms. A nice little trick is we can just go to the form code and view the code, go up to the very top and grab whatever is there and paste it in there, and you'll get it's actually Systems Windows Forms and System Windows Forms is basically what we need for a linked list. So we can just go in here and paste over all these guys, and now we have the ability to have a list box to print to. And what's going to happen is when you are setting up for printing, you're going to create just a temporary pointer that we're going to call current. So I'm going to say node temp, or actually, node current equals head. And the reason why is you don't want to walk the list with your head because you'll lose your head. Because when you walk the list, you're going to be setting current or head equal to heads next or currents next, and therefore head will point over here, and you'll lose your reference to the very start of your list. So we can do a while current does not equal null, and then what we'll do is we'll say the list dot items, the list dot items dot add, and this is the list box, and what we want to do is we want to add the node storage. So since we're using current as something that's going to walk it, and let's go ahead and bring that reference over here so that you guys can kind of get an idea of what I'm talking about when I say current. So this line, node current equals head, basically just said create another reference type, call it current, and assign it to equal to head, meaning it's going to store address 800. So when you say current equals head, you say take that 800 and throw it in what current's storing for an address. And now we have current pointing to the same node as the head is. And we're going to use current to walk, going to currents next each time through. So this is how you walk the list. First, since current is pointing to the head, we're going to add and print the current storage. And what that does is it says go to what the node or the data type that current points to, and it's a node, and inside of it we have the storage, which contains the value 2, and add that to the list box. And we don't have to do any conversions here because storage is an object, but we're using a simple data type, so it should be able to convert to an interval value implicitly. And then once that's done, then you got to walk the list. You got to walk current. You got to say current equals to current dot next. Okay, that's a lot better than head dot next dot next dot next, and using that kind of behavior for getting your information back from our poor man's linked list example. And basically it all works because what happens is current's going to point here, it's going to print the 2 into the list box, then this link basically is redone by saying current equals current next. Current equals current next is holding address 100. So now what ends up happening is this guy is being used to traverse the list, and it now points to the next one in the list, which is this guy right there. Then we print number 1. The loop runs over again. We're on this line. The number 1 is printed. And then we say current equals to current next. Well, current next now is 0. So what ends up happening is 2 and 1 are printed in the list box until current points to 0, which is this guy, is assigned to that. And that's when current hits null and the loop comes out and you're done printing. And that's how a list traversal works. So once current hits that 0 mark after printing 1, this function is done. So let's go ahead and test it out real quick. We'll go here to form 1, and we have mylist.print, and we got to pass it the list box, and the list box is the one that we added in the other video, and this is going to be list box 1, and we don't need to pass anything else because once it has the list box, it's going to be able to add to it. Now when we run and this loads up, we should see the values 2 and 1 printed because current starts out pointing to that head node. Okay, and there's our 2, 1 output. Okay, so then the next thing that we want to be able to do for this is, of course, when we add to the front, we want to be able to move from the front or remove from the front. So we're going to add that bit of code right now, but currently this is kind of what we have. We have a head, a tail. Let's throw in, let's think about adding another number, but we can add that later when we do like maybe add rear and remove from rear. We can kind of get a little bit more items in here to further your understanding. So what we want now is we want to be able to do a mylist.remove front. So essentially what it's going to do is it's just going to take off of the front of the list and remove this item. And that one's actually really simple to do. So what we'll do is we'll go into the linked list manager and we're going to put in public void remove front. Okay, we don't need to pass anything because we're taking things out. And check first, is there anything on the list? If there is, if it's null, then you don't really need to do anything. So you can ignore that and you can say, well, head, or if head does not equal null, only do something if there is nodes on the list. And if head doesn't equal null, then what you can do is you can say head is equal to heads next. And this time you don't want to do a current because you're actually modifying the list. And what you're doing is you're saying go into head, the node it points to, which is address 100, which is this guy, and assign that to head. So what ends up happening then is this link is now gone and this link is now added. And we've lost the reference to this. And essentially what that does in other programming languages is basically it creates what's called a memory leak. And because this is memory that we've declared and created off the heap, therefore we want to be able to have other processes have access to that memory, and we should free it. Other languages, you must free it, but in C# they have a garbage collector that's always looking for references from the heap that our process has accessed and is no longer using, and it clears that up for us. So it's part of managed code. One issue about garbage collectors is it's not really good for game creation because if you are always asking for a new bit of memory, essentially you're always having a garbage collector look to see if that memory is not being used anymore. So what you do is you have what's called memory pooling, where you just grab a whole bunch of memory at the very beginning of your game and use that over and over and over again, and therefore the garbage collector doesn't hit as much. So that is gone, and we no longer have the link and the node, and basically we are now left with one less, or the front removed from the linked list itself. So this takes us into the add rear and remove rear. And since the add front and the remove front do not mess with the tail pointer at all, we can just use the tail pointer as the mechanism for adding and removing to the rear. So essentially, I'm going to move a few things around on this diagram. I'm going to kind of minimize some of this size, and we'll just go with three-digit addresses just to solve this little issue. Okay, so 000. No, that actually is some kind of address, but we don't really care about it too much. It's only what it's pointing to. Okay, and let's draw our links. We have both the head and the tail pointing to the same place. And this is currently the makeup of our linked list with manager. I think I gotta group those. Oh, they're grouped. Okay, that's good. Okay, so it's time to do a add rear. And the same behavior happens when you do an add rear. So there's a little bit of a modification. We're going to take this add front and just copy it and paste it and give it a different name, because we're going to do some of the same steps. Add rear. And we still do this step where we create a new node, and if there's no head is not pointing anywhere, then we still do head equals tail equals new node. It's only here that things are going to change. So let's go ahead and get to the diagram and kind of see what's going on. Our new node, let's go ahead and go back here and let's see where we're at. Okay, so let's do mylist.addRear. And let's type in, let's have it go to 3. Okay, so currently we've written all the code for that. Now we're going to finish up the code for this. And that means that we have our reference point end node come into play. And let's put them on the other side here because we're doing add rear. And I'm going to give this the name end node as a reference point that is currently pointing nowhere. And we will have it point to our new node that is going to contain 3. And let's say that its address that we get from the heap, it looks like I didn't get everything from my selection here. Okay, paste. Alright, so this is our new node that we're adding to the rear. It's going to contain 3. Its next is going to point nowhere. And let's say that the operating system gives us the address of 700 for it. So that means end node is going to point to address 700. And we're pointing in that direction. Okay, so this is essentially where we're at when we get to this portion in the code. All this has been taken care of, and we're now adding another link. The head's not null, and essentially what we want to happen is we want the tail pointing here, and we want the node that the tail was pointing to, its next needs to be pointing to the new tail. So these are the links that we need to make. We need to make this link and this link. Now we don't want to do this one first because tail is what's holding our tail next value, or being able to make that link, because this is currently the tail. So when we add to the rear, we want to make this link first. So essentially what that means is we're going to say go to the tails next and assign it equal to end node. And what that does is it says, okay, end node is storing address 700, which is the new rear, and we want tails next going to it. So that's going to be pointing to 700. And essentially now we've made this link right here. So this one is done. It's good. And the last step is just to say tail is now pointing to new node. And it kind of looks a little weird because when you think about it, you're working with addresses. So when you're using the equal statement, you're assigning addresses, and you want to kind of think of it as pointing to this address. But at the same time, since you're dealing with address, it is actually equals. So get both. I mean, having both those things in your, kind of straight in your mind is the secret to understanding linked lists. And it's pretty much where everybody has their biggest problem with linked lists, is that understanding of pointing to, but also equals, because you're dealing with addresses. So here is where we do tail equals end node. And essentially what we've done is we said take this address and assign it to what end node is storing. And now this link is done, and this link is gone right here. And then when this function gets done running, end node is destroyed, and we're left with just the head and the tail. And this works flawlessly for any other ones you want to add to the rear. It just keeps on getting bigger and bigger, but the same connections are made. Let's go ahead and test this out. When we print it, we should get the values 1 and 3. Let me make sure that we have the print after the add rear. We have the 1, 2, then remove front. So let's go ahead and run this. And we have the values 1, 3. Okay. So the next step would be, let's test it with some more values just to see that, hey, yeah, everything's good. So we should have 1, 3, 4, and 5. There's our 1, 3, 4, and 5. Okay. I think we are good with the add rear. Let's look into how remove rear works, and it's going to be very, very close to the remove front. So let's just take this, copy it. Except for the thing is, when you are dealing with the remove front or remove rear, you have to have knowledge of the previous pointer. So that's where you get into needing, instead of a next, also in addition, a previous. There's a way that we can cheat. We can actually walk the list. If we have multiple items in here, we can walk the list. And let's go ahead and get some different items in here as part of the diagram. But let's reduce some of them. Let's say that we have a 3 and a 4. 3, 4, 5. That's adding 2 more. I think we have the room for it. Let's go ahead and do that. Three, 4. Let's erase this guy. Okay, and then we'll copy for this diagram. Do some Control Z and Control V. Okay, and 3, 4, 5, and let's say that 5 is at address. Let's be simple. Let's say it's at address 500, address 400, and now the next is going to point to the next one, which is address 400, which is the 4, and the 4's next is going to point to the address 500, which is the 5. And essentially what we have then is we have these links. We have head pointing to here, and then we have this link, and this link. And tail is pointing to, we're going to have to change that to 500. Right there, the address. Remember, the addressing is implicit. It's done by the technology. It's not something you have to even worry about. That's what the new returns to you, is the first byte of that address when you ask for memory from the heap, which essentially means all the memory that is free, or all the RAM that is free on your computer. And the operating system is in charge of managing that RAM, and they are the ones that will, that is where the operating system manages where to find the memory and the address to return back to you. And that's why they call it the heap, because it's essentially the heap of memory for everything else. Okay, so this is kind of how our diagram looks, and what we want to do is we want to do a remove rear. So essentially we want to remove this guy right here and have the tail pointing here. So what we have to do is we have to get this address. We don't know what this address is for this guy right here, so we can remove the 5 and have the tail pointing to the 4. But we can walk the list until we get to that node and then make the link. And for that is going to be a for loop that starts at the head or a current node. And let me get to where I'm supposed to be, right there. Okay, so if head does not equal null, then that means that we need to remove from the rear. Actually, you know what? We'll probably better say that head does not, well, actually, let's use tail. Tail makes the most sense. Tail does not equal null. We need to remove that. So that means that we have to walk the list for count -1, which means we need to introduce a counter for our list if we're going to use that for walking. So we're going to call this, and it can be private too, count, assign it to 0 in your constructor, and then what you're going to do is you're going to do a count ++ every time you add a new node and make a link. So in the add front, it can be at the very bottom. Actually, you know what? Yeah, that works. And the remove front, we do a count -. And with the remove rear, as long as the tail is not empty, what we can do is we can say, I want a node called current, and I want to set it equal to head. So let's get our current guy out here. Okay, let's make this one. Now let's copy one that I already have. Let's copy this guy. Call this one current. And we're going to set it equal to head first. So it's already got the address in there, so I'm going to draw a line. And current is going to point here. And we're going to use that to walk the list. And the reason why is because we need to get this guy. We need to get to knowledge of this guy so that we can remove the tail and assign the tail pointer to the new tail. So we're going to use this current variable to get us to that variable or that node. And we can first start it with the head, and then we can use a for loop. And we might have a fence post out here. Basically, you're going to go to I. You're going to start an I loop and go to count -1. We might have to do -2 with the fence post error or off by 1 error, but we'll find out shortly by just testing it. So I'm going to assume that I'm going to basically walk the list and say current is equal to current.next. And what that does is we assign, this loop runs one time, and current is equal to current's next, which is current. Current's next is address 700. So now it points to this guy. The first time through the loop. The second time through the loop, it points to this guy. And that's when count -1 should trigger, and current should be pointing to that one that we have that's of the most interest for our task of removing from the rear. So once this loop gets done running, we should have walked all the way to where current needs to be, and all we got to do now is make some links. And the first link I'm going to make is, since I have a garbage collector and I don't need to worry about freeing that memory up, what I got to do is I've got to assign tail equal to current, and current is currently pointing to address 400. So if I say tail equals current, I still haven't lost this because I've got the next pointing to it, so I can make that link. So essentially that happens, and that goes away. So that's after the for loop, and it's inside the if statement, and we're going to say tail equals current. So now tail is pointing here. Current pretty much we don't care about anymore. It's done its job. It'll be destroyed automatically, so we can, just kind of not even think about it. If I can actually delete it. There we go. So we are left with that, and that's gone. So the way that we end the list, because right now the next of the new tail is pointing to the old tail, so we just basically got to tell it to point nowhere. So you're going to say tails next equals null. Okay, so now when we run this, we're going to have, well, we could have a total off by 1 error and be either to the left or the right of this. So let's look at how it should behave. We have done an add rear of 5. So if we do a remove rear, and the remove rear does not need any arguments. Then we should have a printout, because we've done a remove front. We should have a printout of 1, 3, and 4. And since here I said tails next equals null, that took out this guy and assigned that to 0, 0, or nothing. So it's considered to be pointing to nowhere, and that's, or pointing to null, and that's how you know you're at the end of the list. Okay, 1, 3, and 4 is what we should have for an output, I believe. Let's check it out. 1, 2 is removed, 3, 4, 5 is removed. Okay, let's see if it works. 1, 3, 4, 5. So yeah, we have a fence post. We're off by 1 in the wrong direction. So since we're 0 based, we're off by 1 already. So that means we're off by 2. So that means to fix this, I would do count -2. Let's see if this works. One, 3, 4. Okay, now to make sure this actually works, let's do a add rear of 9 and a add front of 9. So we should get 9, 1, 3, 4, 9. 9, 1, 3, 4, 9. And that's just to make sure that we haven't totally mucked up all of our links. and we're doing everything properly, and there we go, 91349. Okay, so what's next? What's next is the add at and a little bit about remove at. That, and we can also modify this so that we not only have a next variable, but we have a previous. And that's considered a doubly, or basically a double linked list, or doubly linked, both next and previous. So you can go in one direction or the other as you're traversing in the list. There's also making it circular, where you can have what's called a doubly circular linked list, meaning the heads next or heads previous points to the tail, and the tail's next points to the head. So it's doubly linked and circular. And that's where we're going to be heading towards after we discuss the remove, or the add at and remove at. And then what we'll do is we'll make it doubly linked and circular. And that's coming up in the last video on linked lists. All right, for now, thank you. Bye.